Hello, I am Syed Shah. Uh, my key paper review is on the positioning single atom with scanning tunneling microscope (STM). Let's talk about paper. My paper review is on the positioning a single atom with a scanning tunneling microscope (STM). But I will briefly discussing how the tremendous idea about STM were given and then who used the scanning tunneling microscope STM at the atomic level, and then I will discussing how the individual atom will be scaling in the surface. The first paper were given by the development of the family scanning probes microscope started with the original invention of the STEM in the 1981. The great Bennings and English developed the first working STM while working at the IBM Research Laboratory in Switzerland. It was published, and this work is instrument would be later win the Nobel Prize in the physics in 1986. And this work is published in the American Physical Society, and it is now cited almost 9,000 times. So contribution of this paper, second paper was established by positioning single atom with a scanning tunneling microscope, which is also my paper. I am discussing about this paper. In 1919, the Egler and Ahmed operates the SMT to control 35 atoms, single atoms on the nickel surface to create the sign of IBM. It is received in 9th November in 1918 and accepted 16 February in 1919 and published in the Nature of on 5th February April 1918 in volume 344. It is cited near 5,000 times. So the vision of the feminine future prediction that to make the best electron microscope so that there was a progress in the nanotechnology. So early idea of the feminine until 1919, the two physicists have been research to create the ground of the science of small with their discovery of scanning microscope, tunneling microscope. If I talk about this STM, which is the instrument for imaging the surface of atomic level, or we can also say that STM is a technique which are using the sharp tip, which moves to close the conductive surface that atom electron work function in the overlap tips with surface overlap function. Let's talk about the principal idea of that, how it is work. So the principal idea of this is that idea of tunneling can be applied to look at the surface profile of the material at the atomic scale when a sharp metallic tip is brought very close to the surface of a conductor, uh, and electric current can be reduced due to the tunneling of the electronics through the hair gap. And the component of the system include a scanning tip, piezoelectronic control manners, distance controlling, scanning units, vibrations, oscillation systems, and computer record the tunneling currents and control the voltages to the piezoelectronic tubes to produce three-dimensional map of the samples. Let's talk about how the atom's position is. Here I include animations for explaining how a single atom is positioning with a tip through STM. So through this technique, which I discussed in the previous slide, positioning this atom only from random atoms to IBM sand through a single atom selection. So this can be done by the use of STM at low temperature 4 Kelvin to position individual unknown atoms on the surface of a single crystalline nickel surface with atomic precisions. So a tunneling microscope consists of metallic tips with applied voltages. The tip is brought very near to the surface of metallic samples made of xenon atoms. When the voltage is applied between the tip and the sample electron are extracted from the atom surface by continuum tunneling. This creates the electrical current between the tips and the surface. And tunneling occurs only at the very short distance when the tip lies on the top of the uh, atoms. By drawing the current intensity various the tip location, one can reduce the position of the atoms of the metal surface down to the resolution better 0.1 nanometers. By drawing the tips which are creating here the maps. Tunneling microscopes can also be used for spectroscopy. The tip current is now measured various applied voltages. The obtained graphs depends on the electronic properties of the simple electronic at the location of the tip. The tip is moving around the atoms and apply the voltages and measuring the voltages and graph density here. Uh, look like air, it's give the information about the electronic properties of the material down to the nanometer scales. In practice, physics prepare to measure the derivative of this graph, and there's to the tips which are measuring the electrical intensity. Derivative of this graph is shown here. And one can also use tunneling microscope to move the atom. It is our main concern to how one atoms. For example, in some materials, one can bring the tips very close to the atoms, while which is rise to it moves. It's from here to somewhere. It's like it moves from this position to this. This tunneling microscope is there to allow the reconstruct the images of a surface with the atomic resolution, but also to perform atomic spectroscopy and even manipulate the atomic individual atoms. So atomic positionings from random atoms to IBM science. There is uh, a sequence of STM images taken during the construction of a pattern areas of xenon atom on nickel surface. Grayscale is assigned according to the slope of the surface. The atomic structure of the nickel surface is not resolved. The direction runs vertically. A surface after xenon dissolved from B to F. Various stages during the construction. Each data is by maximum from top to bottom, like random atoms to make IBM logo signs. Look, this figure which illustrates the process from sliding an atom across the surface. The atom is located and the tip is placed directly over here, near to the head. In this positions, tip is lower to the position B, where the tip attractive force to the sufficient to keep the atom location beneath to the tip. When the tip is sufficiently moved across the surface C and desired destinations D, finally the tip is withdrawn to the position E, where the atom's tip attractive is negligible, leaving atoms bound and surface of the new locations. Like the tip is select as a non atoms from here to bring B position and to move from C position and to coming here and leave at E positions. There are some drawbacks such as the use of the systems at high ultra vacuum systems, cooling port Kelvin temperature. This could entire chamber, keeping a microscope to 4 Kelvin, minimizing the rate of contamination to simple surface by the absorption of residual gases that did not occur our weeks without observable contamination. So because of the low temperature, the stability of the sample and the microscope is such that one can conduct experiment on a single atom for a day at a time. It is also high ultra vacuum stem which are not easy to build and handle. The stem can be conductive surface of thin nano conductive films and small objective deposit of a conductive substrates. It did not work in the nano conductive materials such as glass and rocks. State-of-the-art approaches like manipulating single atoms with electron beams. And now the scanning electron microscope is able to readily focus on electric beam with subatomic precisions, allowing scientists to directly see each atom in two-dimensional material like graphenes. Here is the show the interesting video. Uh, in this video, electronic beam focused on carbon atoms next to the silicon impurity atoms can contributably make it jump to where the beams was placed. Step by step, this allows silicons to move with atomic precisions around the external paths. And here is the atom moving from one place to another place. And existing work for SMT is insulatic tunneling induced manipulation by using the insulatic electrons. This can use tunneling, low energy tunneling electrons or holes injected to the atom molecules, location of the surface by positioning a tip above the target. The current work is on design scanning microscope to low temperature, which are designing for emissions region, spent for relations at 77 temperature, Kelvin temperature. The example of this current positioning of a single atom is magnetic data bit stored on a single bit, and the second example is binary atomic silicon logic. The IBM researchers say it is the smallest. The first example is the smallest memory, which we are made a magnetic memory from 3 to 12 atoms to make a memory. And the binary atomic silicon logic is the method we have been used to render digital component known as logic gates. Manipulated circuits could be eventually be pulled from single atoms. And the conclusion that The spectral resolution of SMT is fantastic, but the temporal resolution is typically on the order of second, which will prevent the SMT from imaging fast kinetic of our electrochemical process. Thank you.